Hello again, and this lesson I'm going to be looking at some practical applications, or trying to answer the question, why do we do calculus? Or as I like to say, why do we do calculus? Hey? So, let's have a look at some practical applications of using derivatives. This first example, we've got a loop of string of length 200 centimeters, and it's going to form a rectangle. Find the maximum area of this rectangle. So, here's my loop of string. Don't know how long it is. Let's call it X. And, oh, no, we do know how long it is. It's 200 centimeters. Silly. It's 200 centimeters long. And when we form a rectangle, we're going to have different measurements. Oh, that didn't work, did it? We're going to have different measurements. So, if we can look at this, we'd have X and Y. And so, for this one, we can say the perimeter would be 2 lots of the length, so 2 lots of X plus 2 lots of the width, 2Y, which equals 200 centimeters. Then, if we can try and find a way of rearranging or solving this, we need to get it down to one variable. So if we look at 2x plus 2y, we'd say equals 200. Let's rearrange to find y, so we could minus the 2x over, and we get 2y equals 200 minus 2x. So if we divide everything by 2, we end up getting 100 minus x. So now we can write this as 100 minus x for our width. So now we have a rectangle purely in terms of x. How do we find the maximum area, and what x value is that going to give us? So let's move our second example down, gives a little bit more space. We know the area of a rectangle, well, we hopefully know the area of a rectangle is length times width. So for this, area is going to equal xy, and we know y is 100 minus x. So now we have a formula for the area, and let's expand the brackets out. It'll come in handy when we have to derive. We have area equals 100x minus x squared. So if we look at the derivative, dA dx, and now you're finally realizing what I meant by dy, do we do calculus? We get 100 minus 2x. So that tells us the derivative for the area in terms of x. We need to find the maximum, and we know the maximum is a stationary point. So dA dx equals 0. So dA dx equals 0 is when the maximum is going to occur. So we solve for 100 minus 2x equal to 0. And we end up getting minus 2x would equal minus 100 divided by minus 2 would give us x equals 50. So that tells us that the x value here, or the length, must be 50. And so then 100 minus 50 is also 50. So the maximum area actually occurs with a square, which by definition fits the rectangle 50 by 50 centimeters is going to be your maximum area, which would give us 2,500 centimeters squared, which is your maximum area. Okay, let's look at another problem here, and you might go, well, how often am I playing with string and just making shapes for the sake of it? You could extend that to fencing, some real life sort of practical stuff and properties, but this example here is looking at making a box. And you think about any distributor that's going to be making packaging for their product. Obviously, they want to fit the most in the smallest amount of materials, save on costing, lessen the environmental footprint, and all of these other sort of altruistic goals. So here's a sheet of metal, and you see they've cut out the corners so they can fold it up and make a box out of it. All right, the square piece that started with had a length of 6, and then 4 squares are removed from the diagram. The metal fold along is to form the dashed lines open box with a height of x. So I'm just going to draw that a little bit bigger. There's our shape, and what we know is originally it was 6. So 6 goes all the way across there, and it was a square, so that's 6 as well. And then when they cut it out, they cut out X amount, because when we fold it up, we have a height of X. There it is. So that's what our box looks like. So first question says, show that the volume V is given by this formula. So let's just work out V and see if we get the same answer. We've got lengths here. For the volume of a rectangular prism, it's going to be length times width times height. So length, width, height, doesn't matter what we call them, because they're all multiplying, it's commutative. So the order does matter. So length times width times height, we know the height's already X. So that tells us one of those is X. And we want to find L and W in terms of X. So if we look at our original box at the top here, we know 6 is all the way across. If there's X cut off from there and X cut off from there, we can say that this distance must be 6 minus 2X. And then same for this side, 6 minus 2X, because we've got one lot of X there, one lot of X there, cut off. So we end up 6 minus 2X. So we could write this as 6 minus 2X times 6 minus 2X. It's going to be squared times X. So let's expand that out. There's our formula for V. We'd end up getting 6 squared is 36. Two lots of negative 2x times 6 would be minus 24x, and then minus 2x all squared would be plus 4x squared, and then we've got to multiply that by our friend x at the end. I'm just going to start putting these in the highest order power, so 4x squared times x was 4x cubed. Then I'd have minus 24x squared plus 36x, and hopefully we got the same as what was asked for in the question. Looks good. Last part, find the value of x that gives the box its maximum volume and find the maximum volume. So similar to our first question, we're trying to find out, alright, what value of x would give this shape the most volume? So therefore, if it's a packaging thing, the most stuff I could fit in there. So this is a metal side, so I don't know what they're making out of metal boxes for, but a chest or a pool or something like that. So let's find the maximum. Now the maximum is a stationary point, so we know the derivative dv dx must equal 0. So max when dv dx equals 0. Now, key thing to remember before we start here is 6 minus 2x, for this to be a physical thing that we build, the maximum value of x can't exceed where we're going to end up chopping off more than we started with. So if x was 3, we'd have 6 minus 6 over 0. Okay, so x has a maximum of 3, and we can't cut off a negative amount, because that means we'd be somehow pasting metal back on, and that's not the way it works. So we say x is going to be between 0 and 3. That might help us if we find, for this formula, there's going to be more stationary points that might be outside that range that we're just going to have to reject. So dv dx equals 0, let's solve it. So first of all, let's find our derivative. So dv dx is going to be 12x squared, dv dx, minus 48x plus 36. Solving that equal to 0. And you go, oh, that looks like a very mean non-monic trinomial, but we've got a factor of 12 through all that. So let's divide all of those by 12, divide by 12, divide by 12, divide by 12, divide by 12. We end up getting x squared minus 4x plus 3 equals 0. So factors of 3 that add up to negative 4. So it'd be negative 3 and negative 1 equals 0. So therefore, we have stationary points at x equals 1 and x equals 3. Now, when we look at that, remember we said that x couldn't be between, or couldn't be bigger than 3. So we'll have a look at this and go, at the volume, if it was 3, that means we're chopping off the whole thing. The volume's going to be 0, isn't it? So it's clearly not going to be the maximum. Alright, so it's just thinking about if I had my sheet metal here and I started with 6 and then I cut off 6, I'll draw you a picture of a box. Alright, so here's our box originally. Alright, you'd end up getting a box that looks like this. So there's my picture, I've just underlined it. That's right, it's nothing. There's no box. Volume equals 0, because you cut it all the metal off. It's just a flat piece of metal. Alright, So, therefore, the maximum must be at v. Therefore, max at x equals 1. So the last thing is to find the volume when x equaled 1. So we put that into our volume formula, which was the 4x cubed minus 24x squared plus 36x. And even if you stuffed up the derivative, that was given to you in part A. So we can just plug in 1 into that, and we should get, let's have a look, 4 times 1 cubed, 24, 36, minus 24, 1 squared plus 36 times 1. So you get 4 minus 24 is minus 20 plus 36 is 16. So that would be 6 meters cubed. Or centimeters cubed, is it? Centimeters cubed. Okay. Let's have a look. Oh, no, it's meters. Oh, it's big. All right. So 6 cubic meters is your maximum volume when x equals 1. Okay. So hopefully you can have a go at some of those application type questions. Most of them should be able to do by hand, and we'll look at some trickier ones with calculators in the next lesson.